Okay, so we'll come to that. Okay, these are the questions that you have to ask, okay, before designing any, before choosing any conveyor system. Okay, these are the factors to be taken into account. Okay.
Look for conveyor features that secure or enclose the material or product onto the conveyor. Will moisture be present in the application? Does the application need to be sanitary? Here, look for rugged or washdown rated conveyors with open frames. Most conveyors in light and medium duty discrete transport applications use belt that's wrapped around two or more pulleys. A motor powers the pulleys that in turn engage the conveyor belt. Belt styles and materials abound to meet specific applications. Some belts are low friction, so product can slide a bit for accumulation. In contrast, high friction belts have more grip to better hold products. Engineers can design such conveyors to meet exact application specifications. Timing belt conveyors use tooth belts that engage synchronous drive pulleys while serving as the conveyor surface as well. These provide excellent belt movement control for accurate part or fixture positioning. Magnetic conveyors are built with ceramic magnets for applications needing parts to adhere to the belt during processing or for jobs that require elevation changes. Higher magnet strength serves inverted applications. Vacuum conveyors work with a perforated belt that draws air through grooves in the conveyor bed plate to hold light or flimsy parts on inclines or during especially fast transport. Some
That was your vacuum type of system. Okay, conveyor system.
flimsy parts on inclines or during especially fast transport. Some metal-free conveyors have polymer bed plates instead of steel bed plates where metal scanning equipment checks product, usually food, for contaminants. Last but not least, pivot conveyors mount to a base to swing away when workers need to walk through a line. Some controls can automatically resume product flow after conveyor returns to the inline position. Where the conveyor takes the form of a timing belt conveyor, servo drives accurately stop and start the setup to provide precise part location. They also let engineers control acceleration, so work for conveyors that serve assembly lines. Encoders on a conveyor's drive shaft sense shaft rotation or count pulley revolutions for belt control in feeding or indexing. In sum,
So these are all things that you have to consider, right? Because we want to have this data communication, right, between the servo system driving the conveyor system and the different machines, also machine transfer lines, right? So counting the pulley revolutions and rotation of the shaft, right, how much is the shaft rotating, etc. So that's about that, and I believe there's nothing more here. Okay, so this is clear, right? Conveyor system, what you need to consider before selecting any type of conveyor system, right? So okay, so Geneva mechanism we saw, right? Now yes, there's a problem on Geneva mechanism, so we could expect a problem. It's very rare, but let's look at it. Okay, it's a very simple problem. So we saw the Geneva mechanism. You had a driver, right, and this driven member. So theta is the angle of rotation of work table during indexing, 360 by ns. Okay, theta. What's ns? Ns represents the number of slots in the Geneva mechanism, right? As for example, here we saw 6 slots. So ns represents the number of slots. So if you divide 360 by the slots, as I told you, you'll get this rotation of the driven member, right? So 360 by ns, let's say 6 slots we had. So 360 by 6 will give you what? 60 degrees. So 60 degrees is the angle of rotation of the work table, isn't it? Because the work table will be moving because of this driven member. It is above this driven member that you have the table, right? So 60 degrees is what the table will move. So that's the angle of rotation of the work table. N as we saw. TC, what is TC? Is the cycle time in minutes. So you see TC is 1 by N. And what is N? N is the rotational speed of driver in revolutions per minute. So we have this terminology, right? RPM, 200 RPM, 300 RPM, revolutions per minute. So if we are using a motor okay, which is used to drive this driver. Okay, the driver is driven by some motor whose RPM is 200 RPM. Okay, 200 revolutions per minute. So that will give you n, and if you reverse that, you'll get the cycle time. That is basically in minutes, because we are taking n is revolution n in revolutions per minute, so you get it in minutes, TC, cycle time. So that's about that. And TS is the available service or processing time, or you can also call it dwell time. Okay, and TR is the indexing time in minutes. So we'll see that. You'll get the idea of what exactly it means with this example. Okay, so you see, a rotary work table is driven by a Geneva mechanism, right? We know that to drive that rotary work table, we are using this Geneva mechanism. So with six slots, okay, it has six slots. Okay, we are taking exactly this example, six slots. So driver rotates at 30 revolutions per minute. Okay, that's the rotation of the driver. Determine the cycle time, available processing time, and the lost time each cycle to index the table. So if we know the driver rotational speed, that is 30 revolutions per minute, we know the total cycle time. Now you'll get the idea what is the total cycle time. So 30 revolutions per minute is the speed. So if you want to get TC, 1 by n, 1 by 30 or 30 inverse, right, we'll give you this in minutes, right? Because we used RPM, revolutions per minute, we'll get it in minutes. We want to convert it into seconds. 1 minute is 60 seconds. So you multiply this by 60. You get 2 seconds. So basically, it is the total cycle time. So you see, um for every 2 seconds, okay, the table will move. Basically, that's what it means. Okay, because the and you have to observe that the cycle time depends on n, only n, right? TC depends on n. Higher the n, higher will be your what do you call, I'm sorry, lower will be your cycle time, because they're inversely proportional, right? So if the driver rotates at a high speed, you have less cycle time. So for every, instead of moving for every 2 seconds, it will move for every 1 second, right? Higher if the rotational speed is higher. So that's what it means. Okay, just to give you a physical sense of what it means. So angle of rotation of the work table during indexing for a 6 slotted Geneva, right? Theta. How do you calculate theta? 360 by ns. Ns is the number of slots. So we have 6 slots here as per the data given in the question. So that gives you 60-degree angle, right, of the work table. Basically, the work table will move by 60 for every indexing. Okay, so we want to know available service time and indexing time. So that's your formula there, right? So when you put that, if you observe, if you add these two, what do you get? If you add these two, denominators are same, you get 360n, and okay. So you see, if you add these two in the numerator, uh, theta gets cancelled. Okay, plus and minus. So 180 plus 180 gives you 360. Okay, and divided by, you have this 360 at the bottom, right? So that cancels, isn't it? And where do we have that? Yes, here you see, if you add these two, what do you get? You get 2 seconds, right? That's your total cycle time. So basically, we are trying to know what is the service time and what is the indexing time. So that is basically how can we put it, that you see the driver engages here, right? That's basically where your uh, TS time starts, available service time. Okay, TS starts here, we count it, it moves up here, and here TS stops. Okay, so that's the time taken for the driver to rotate this work table, and the remaining time is your this time, TS. I'm sorry, TR. Okay, so if you sum these two, you'll get this, isn't it? So that's your available service time and your indexing time. Okay, very simple. You have these basic formulas, but you have to get a sense of what it means, right? So if you understand the mechanism, you'll get what we mean by this TS and TR, indexing and service times, isn't it? This is clear, right? Geneva mechanism and the problem that we saw. Okay. Another one is your CAM mechanism. This is all. This also comes under your rotary transfer mechanism. So provide probably the most accurate and reliable method of indexing the dial. They are in widespread use in industry, despite the fact that the cost is relatively high compared to alternative mechanisms. CAM can be designed to give a variety of velocity and dwell characteristics. So that's why it makes it. That's why it makes it more popular. Because it is high, the cost is high because you see, to get that characteristics of velocity and dwell, like how much to move and how what do you call, the speed at which it moves and the precision that you get in CAM mechanism is quite high. Okay, so that's what makes it costly. The design of it is costly, therefore the mechanism is costly. So but still it is the most accurate and reliable method. You see here, just like your in that cam and follower, right? You have this one here, that this slot in the cam, okay, is guiding these, what do you call, uh, followers, you can say. Okay, so as this cam rotates, it'll engage with these buttons here. Okay, and that'll move the plate. Okay, that's how it works. So there could be many ways of doing it. Like here you see, if you rotate this what do you call, shaft is uh, is engaged with this, right? So this moves linearly. Why? And the way it moves is based on this profile. As it rotates, it has to follow this, right? Because it is engaged with this, it has to follow the profile of the cam, right? This profile. So the motion of this, linear motion of this, is decided by this profile here. So that's what makes it more popular, that you can change the profile and that changes the way this moves. Okay, and another one is this, right? So if it rolls over this, as per this profile, this will move up and down like that. Okay, so that's how we are able to convert this what do you call, motion of the cam to this motion of the work table. Okay, well, I don't have the video of it, but I hope this is clear, right? Cam mechanism, quite simple if you understand it. The rotation of this cam, and because of this profile, it is engaging with the buttons and the buttons move. Okay, this profile is making these buttons move in a rotating fashion, circular fashion. That's what moves the table. Okay, and that's how we're able to achieve the indexing, right? So control functions, you see three main functions that we are utilizing, because there are three things that we want to control. Okay, in an automatic transfer system. First is your sequence control, that is your operational requirement. So we want to coordinate the sequence of actions. We have a sequence, as we know, in machining transfer systems the operations has to be performed in sequence. So to be able to coordinate that, okay, we have to have a sequence control. Various activities of the automated flow line must be carried out with split second timing and accuracy, right? We were seeing in that bottle filling, for example, right? How in split second that bottle moves and we are able to fill it in the nozzle. So split second timing and accuracy. So, and sequence control is basic to the operation of any flow line. Okay, because we are basically trying to implement different operations, right? We are trying to integrate different workstations, so you have to have a sequence control. And safety monitoring ensures that this transfer system does not operate in an unsafe or hazardous condition, right? Safety monitoring, as the name suggests, we are trying to ensure that there is safety while it is being uh, while the machining is being done, for example on a machining transfer line. How do you do that? With the help of sensing devices, okay, to make certain that the cutting tool status is satisfactory to continue the process the to continue to process the work part in the case of a machining type transfer line, right? One example of it, in a machining type transfer line, you have to ensure the cutting tool status. So safety monitoring, other checks might include monitoring certain critical steps, okay, in the control sequence control function, to make sure that these steps have all been performed in the correct order, right? You have to ensure that the steps that you are doing have been performed in the correct order. And hydraulic or air pressures might also be checked if these are crucial to the operation of automated flow lines. So because the automated as we have seen automated function systems utilizes hydraulic and pneumatic devices, so you have to ensure that those pressures are also correct, right? And then you have quality monitoring. So it's already 3 o'clock. Okay, if there are any doubts so far, you can ask, otherwise we'll end the meeting. Okay, then I'm ending the meeting. Thank you.